This video describes and analyzes the drug delivery experiment performed by Team 14, Marissa Bach, Andre Losa, and Alyssa Pern. Pharmaceutical production and design is a trillion-dollar worldwide industry that assesses some of the most challenging problems regarding global healthcare. As such, they hire a high number of engineers to deal with the technicalities and specification that is required for successful treatments. One such factor is drug delivery, the rate at which the drug is administered once it is inside the body. This can range from a fast-acting and high-dosage pain reliever to a continuous low-dosage hormonal regulator such as contraceptives. As engineers, we use beads to model vesicles and dyes of known concentration to model the active agents. Monitoring and quantification of the rate of dye release into liquid water allows us to understand the laws governing such a phenomenon. In this experiment, the polymer alginate was used to cross-link the dye tartrazine representing a drug. Alginate is commonly used as a cross-linking agent in pharmaceuticals due to its biocompatibility. Here, sodium alginate was exposed to calcium ions in the presence of tartrazine. The alginate folds around the calcium ions and the tartrazine is encapsulated within these folds. The alginate beads cross-linked with the dye tartrazine were placed into a beaker of water and stirred such that the tartrazine would diffuse from the beads into the water. This diffusion was monitored by measuring the amount of dye in the water via spectrophotometry. This system simulates the release of a drug cross-linked with alginate in the body. Fick's second law of diffusion relates the change in concentration over time to the concentration gradient in the diffusion coefficient. The Ritger-Pepos equation is an empirical mathematical model applied to drug release kinetics. F is the fraction of dye released, or mt, the mass of dye released at time t, divided by m infinity, the total mass in the beads. K is the kinetic constant, t is the time of dye release, and n is the diffusional exponent for drug release. Analysis of the Ritger-Pepos equation leads us to determine a theoretical diffusional exponent, which indicates Fick's diffusion at 0.43 for Spears. The Ritger-Pepos equation can be linearized using natural logs to determine the coefficients from experimental data. The normalized rate of release can be observed by calculating the change in fractional release over time. The diffusion experiments were performed at varied temperature, stir rate, and bead size to observe the effect of each on dye release. It was predicted that the diffusion rate would increase with increasing temperature, increasing stir rate, and decreasing bead size.
Materials and methods.
0.5 grams of tartrazine was dissolved in 1 liter of water to make the dye solution. Then, 3 grams of alginate was added to 300 milliliters of the dye solution to make a stock solution of the alginate and dye. The calcium chloride solution was prepared by adding 43.17 grams of calcium chloride dihydrate to 500 milliliters of water.
To make a standard curve, a series of dilutions are made. The initial 1:50 solution of tartrazine is made by diluting 100 microliters of the 0.5 grams per liter solution into a final 5 milliliter solution. This is done by using 4.9 milliliters of distilled water and mixing using the pipette tip. Two milliliter aliquots are further diluted and mixed with 2 milliliters of distilled water to make the display fractions, which include 50, 100, 200, 400, and 800. 1 milliliter aliquots were measured and placed in cuvettes. Their adsorbents were measured using the spectrometer at 427 nanometers. This method was used to obtain calibration and experimental data.
By plotting absorbance at 427 nanometers versus tartrazine concentration, a relationship between recorded absorbance and tartrazine concentration was determined. The linear regression generated from this calibration curve could then be used to analyze experimental samples.
3 milliliters of the alginate tartrazine solution were suctioned with a syringe of specified gauge. Droplets were introduced into the calcium alginate solution by freefall with a perpendicular syringe. They were allowed to polymerize for 2 minutes and 19 seconds. After polymerization time, the beads were segregated using a coffee filter and sprinkled with water. The resulting beads were then loaded into a 500 ml beaker with distilled water and known stir rate and temperature. Aliquots were measured at 2-minute intervals for the first 10 minutes, 5-minute intervals for the following 20 minutes, and 10-minute intervals until the 1-hour mark.
Results and analysis. The first manipulated variable was temperature. After collecting all absorbance data, plotting absorbance versus time allowed for the general trend of the effect of temperature on tartrazine diffusion to be determined. For an in-depth analysis, absorbance values were related to tartrazine concentrations using the calibration curve equation. From the calculated tartrazine concentration, the total mass of tartrazine released at each time point could be determined. By comparing this value to the mass of tartrazine loaded into the beads, represented by M infinity, the release fraction could be determined. The cumulative release fraction at each time point for each experimental group is plotted here. Note that the release fraction begins to plateau around the 30-minute time point, indicating that the maximum amount of tartrazine has been released. The normalized rate of release, df/dt, could be determined from the calculated release fractions. Using a linear approximation, the slope of the fractional release curve at each time point could be determined. These calculated df/dt values are plotted here. Note that tartrazine release is rapid initially, but decreases exponentially until the rate of release approaches 0. To allow for determination of n and k parameters, a logarithmic plot of the natural log of f versus the natural log of time was generated. The first 15 minutes of data were used to fit the data linearly for each experimental group. The slope of the line of the linear regression represents n, and the y-intercept represents the natural log of k. From this equation, n and k could be determined for each experimental group. The following table shows the calculated n and k values for each group. Based on the value for n, the type of transport could be determined. The second manipulated variable was stir rate. After plotting absorbance versus time for each experimental group, the same methods of analysis were used for this variable. The cumulative fraction of tartrazine release was plotted as a function of time, and the normalized rate of tartrazine release at each time point was also plotted. Finally, the plot of the natural log of f versus the natural log of time was used to determine the n and k parameters. Again, the first 20 minutes of data were used to fit the data linearly. The slope of the line represents n, and the y-intercept represents the natural log of k. These are the calculated parameters for k and n, as well as the associated type of transport, determined at 50 rpm, 150 rpm, and 300 rpm. The third manipulated variable was bead size. Different size beads were produced by using a 16-gauge, 19-gauge, or 22-gauge needle. The actual bead diameters were measured to be 3 mm, 2.5 mm, and 2 mm, respectively. As before, the absorbance versus time for each experimental group was plotted. Then, the same methods of analysis were used. The cumulative fraction of tartrazine release was plotted as a function of time, as was the normalized rate of tartrazine release, calculated at each time point. Lastly, the plot of the natural log of f versus the natural log of time was again plotted to determine the n and k parameters. The first 20 minutes of data were used to fit the data linearly. These are the calculated parameters for beads prepared from 16-gauge, 19-gauge, and 22-gauge needles. The following are the conclusions drawn from each experiment. After analyzing the data, the effect of the manipulated variables on different factors of tartrazine release, including the release fraction, rate of release, and k and n parameters, could be determined. For temperature, it is apparent that at a higher temperature, the overall release fraction, rate of release, and k are higher. However, there is no apparent effect on n. Thus, it appears that increasing temperature increases the tartrazine release by affecting the diffusion constant of tartrazine. For stir rate, although the release fraction and rate of release are greater at 150 rpm than at 50 rpm, the release at 300 rpm is less than that at either of the other two speeds. Outside factors, such as dye being absorbed into the filter paper, likely affected the results of the experiment. The results are therefore inconclusive, and the experiment should be repeated. Similarly, for bead size, while a 16-gauge needle had a greater release than a 22-gauge needle, the 19-gauge needle had a lesser release than the other two groups. The results are therefore inconclusive, and the experiment should be repeated.